Alright, so we're going to look at number systems today.
Definitely.
Decimal number system.
So the base 10?
Yep, which is a base 10. The base really means we've got 10 different symbols. So the symbols in decimal are the symbols 0, 1, 2, right through to 9. And if we were to count higher than 9, we need to use more digits. So if I were to go to the next digit after that, it's 10.
Yeah.
Next number after 9 is 10, which has 2 digits. Okay, so we've got 10 different symbols, 0 through to 9, and if we want to count higher than that, we use more digits. And if you have a look, I'll do it in a column. So we go to the next one, which is 10. You can see the 9 clocks back around to 0, and 11. Now we're just sort of repeating this pattern again. What we've done is, we haven't shown the number here, 0, but it's, if I were to write these as digits, there's a 0 as the first one, and then once we get to the run out of the last digit, so we've run out of digits here, we clock that round back to the beginning again, and we increment this one by 1. And so you can imagine what happens when we get down to 99, clock over the 9, which makes that back to 0, makes this one clock over 1 again, which brings that one back to 0 again, and the third one will then clock over from 0.
So once it reaches the 0, you just increment the 1 on the left hand side.
That's right. Yeah. In electronics, we might have a problem with this because we've only got 2 states. We don't have the 10 different symbols that we can use, so we've only got the 2. Examine what would happen if we only had those 2 states.
First state.
So why is it only 2 states?
Why is it only 2 states? It's because we're looking at the voltage level. In electronics, we define the high voltage as logic 1, and the low voltage is logic 0. So we've only got the 2 voltage levels that matter, and that's the close to the supply voltage and close to 0 volts.
So pretty much like low and high?
Low and high, on or off.
True and false, yeah.
True or false, they're all analogous to the same thing. They all mean either 0 or 1. Base 2,
For electronics.
which is binary. So we've only got the 2 symbols now, so we don't have the 0, 1, 2, right through to 9. We've only got 0, 1. So now, if I want to count up to the next digit, which is 2, in decimal, I'm going to need to use 2 digits.
Yeah.
Okay? This one is equal to 0, this one's equal to 1. And to count up the next one, I've run out of digits, so I'm going to reset it back to 0 and increment the next one by 1.
Like what you did before. Yeah.
Like exactly what I did before when I got to 9, except now I don't have 9, I've only got 1. 0 and 1, and then I increment the next one up to get to the next one. And if I repeat the process, increment that again, increment this one, which go back to 0, which makes this one increment, which brings back to 0, and make the next one increment, which makes it 1. And this would equal 4. Examine how this might come into account with something like a counter. Okay, so now we want to convert between these 2 numbers, so let's show how to do that. Now there are 2 different ways we can do it, and both of them are the same idea. One might be quicker than the other, one might be more intuitive than the other. So I'll show you both ways. So the way that you can do it is looking at the remainders by dividing by 2. So let's do an example. Let's do
35
as my decimal number, and this is how I'd show that. That's what I'm referring to. Put a little base 10.
Yep.
Okay, and that's going to be equal to something which we're going to work out with the base 2. So what I'm going to do with the remainder system, so this is the remainder process. I'm going to divide this by 2 each time, and each time I divide by 2, well, if it's an odd number, there's going to be a remainder of 1. If it's an even number, there's not going to be a remainder of anything, because if it's even, it divides by 2 perfectly. I'm going to write down the remainder from right to left. So the first one, we divide by 2. First one, 35 divided by 2 is equal to 17. 1. Okay, so I'm going to write down the 1 there. 17 divided by 2 is 8.
Remainder 1. Another 1 there.
8 divided by 2 is 4.
Remainder 0. 0 here.
4 divided by 2 is 2. Remainder 0.
0.
2 divided by 2 is 1.
Remainder 0. Okay.
And 1 divided by 2 is 0. Remainder
1.
Okay, so now this is my least significant bit. Let's break this down into how this might actually convert from binary through to the decimal. So if I start at this end, this means how many 1s have I got? Same way that 35 here means we've got 5 lots of 1 and 3 lots of 10. And if I had another digit there, I'd have that many lots of 100 and so on. 1s, 2s, 4s, 8s, 16s and 32s. So I've got
1 lot of 1 plus 1 lot of 2. Let's just write out. 1 lot of 1 plus 1 lot of 2 plus 0 lots of 4 plus 0 lots of 8 plus 0 lots of 16 plus 1 lot of 32. Okay, so we've got 1 plus 2 plus 32 is equal to 35.
back to what we had before.
Oh, okay.
Okay, so this is the remainder process to get from a decimal to a binary. So I would write this
1 0 0.
starting from the most significant bit on the left, 1 and 3 zeros.
1 1.
Okay, so 35 is
1 0 0 0 1 1. Basically.
So you pretty much just divide the number by 2,
yep.
and then you just record the remainder.
Record the remainder and repeat the process. And that's actually how a microcontroller does that. So a computer or something has a circuit internally that would do a decimal to binary conversion in this fashion.
Out of the 2 methods you're describing, this method is what is done by the microcontroller.
Pretty much, because it's cyclical. I could take any size number and I just have to repeat this whole process
Algorithm, yeah.
as many times as I need to. And for a computer it can do it very quickly. So going from decimal to a binary using the remainder process, and we can see by using the powers of 2 process, which is this one, to get from the binary to a decimal. Now the other process is the powers of 2 process with a decimal number. They call it the place value system. You've got to pick a number.
2,143.
Now I purposely chose all the digits to be different so I can talk about each one. So what this really means is I've got 3
lots of 1, so I've got 3 lots of 1. I've got 4 lots of 10, which makes it 40. I've got 1 lot of 100. And I've got 2 lots of 1,000.
When we write down a decimal number like this, with the several digits, then each number on the left has a greater weighting, and it's a greater by a factor of 10 each time. We can look at that.
1 is 10 to the power of 0, 10 is 10 to the power of 1, 100 is 10 squared, and 1,000 is 10 to the power of 3.
And all I do to get my number here is I look at how many lots of each one I need. Now we can tie that back into our binary number. I already know that I'm going to have
1s, 2s, 4s, 8s, 16s, 32s.
the next one will be 64 because I'm just multiplying. So I start at 1 and I multiply it by 2 each time.
So if it was just a normal decimal system, it would be in like times by 10. So 1, 10, 100,
Yeah,
1,000.
that's right. The 1s, 10s, 100s, 1000s.
And so with this one, you just timesing by 2.
That's right. So
Yep.
I'm using the powers of 2. If we look at actually where these come from with the powers of 2.
This is 1 is 2 to the power of 0, 2 is 2 to the power of 1, 4 is 2 squared, is 2 cubed.
And what do you think 16 is?
2 to the power of 4.
2 to the power of 4. You can see this pattern here, 0, 1, 2, 3. Every time we go up, we're increasing the exponent here
Yep.
of our power of 2 by 1.
So 2 to the 5th and 2 to the 6th.
Get from my decimal number of 35 using the power of 2 method. What I do is I look at and see if this one will fit into one of these numbers, and if it's larger than this number. So if it's larger than this number, I put a 1 down and I subtract this number down from it. So is 35 larger than 64? No, it's
No.
not. So
0, so leave it.
is 35 larger than 32? It is.
So I put 1 and I subtract this power of 2 from it. So 5 minus 2 is 3, 30 minus 30 is 0, so we're left with 3.
So now we're going to test to see if this number is bigger than this one. It's not.
No? No. No.
Okay, it is now.
So then we subtract it. So 3 minus 2 is 1.
And is 1 greater than that? Well, or greater than or equal to? It's equal.
Yep.
So put 1 there, subtract the 1 from that, and 0. Okay? And
So now we're back. This one should always end in 0. And we can see we get exactly the same binary number as we did before. Okay? And if you become quite adept at this can be quite quick because you don't need to write this all out. You can do it in your head nearly. Okay, so I go, oh, right, the next smallest one, power of 2 below this one is 32, left over is 3, so I've got to go a while before I get to that, and I can nearly do it in my head. Okay, so it's a much quicker way if you remember these numbers.
Let's see how good you are then. So what if I gave you 25?
25?
Yep.
Okay, so the next one below that's 16. So we've got 16. Take that is 9, so we've got next one below that's 8. Below, that's left over with 1, so we're going to have no 4s, no 2s. Let's
Nice.
just check it.
Yep.
So we've got a 16 plus 8 plus 1. 16 and 8 is 24 plus 1 is 25.
So it just seems like this way is quicker than the
It
last
is much quicker if you know these really well and the number's not crazy big.
Yeah.
Okay? So 25, doable. If you ask me 532,
Gets a
I'd
bit
struggle
tricky.
a little
Yeah.
bit. I can still do it, but it would just be, I probably would need to write it down.
I think this is the main
still,
concept.
I
so-
find this one way quicker than the remainders method.
Yeah.
Okay? Both of them are quite valid ways of solving this, or converting from a decimal to a binary.
It just seems like the way you want to do it is to learn the first step first, and then when you're confident with it, then use the second step.
Yeah. Now, the remainders method also works a little bit better for if you want to convert directly between other number systems. So if I want to convert between decimal and octal, for example, then the remainder system is much better than this one. Because I don't remember my powers of 8 with the power of things.
Yep.
So it's going to be a bit difficult. We don't just have decimal and binary, we have two other number systems. Two other number systems, octal, hexadecimal. Octal has a base of 8. Back again, symbols are,
0 through to 9, 0 and 1.
and in octal the symbols are 0 through to 7.
So why is it 7? Shouldn't it be 8 maybe?
Well, there are 8 separate symbols there. 0, 1, 2, 3,
Up to 7.
up
Yep.
to 7. Okay, so I'm always including 0. Hexadecimal is base,
16.
which is 0 through to 9.
Then A, B, C, D, E, F.
We write with capitals, so we've got 10 symbols there and a further 6 there to make up the 16.
So the letters themselves have
The
a...
letters themselves count as a number, so A
Yep.
counts as decimal 10,
Oh,
B
okay.
counts as decimal 11, C counts as decimal 12.
all the way to 15.
Right up to 15.
Yep.
And then if you want to represent a number bigger than 15, you're going to need two symbols. In the same way that if you want to represent a number bigger than 9, you need 2,
For decimal.
1 or 7 or so on. I find it much easier to convert, if I've got to convert from decimal to one of these, I convert the decimal to binary first. Okay? It's much easier because binary to octal and binary to hexadecimal is really, really, really easy. So I'll show you how to do that.
Alright.
So binary to octal,
Is this the only way to do it, or...?
not the only, but probably, oh, to binary to octal, yes. Well, it's not the only, but it's the easiest way.
Alright. So we'll just stick with this way then.
Yep, it is simply, and it is so much easier. Okay, so let's just pick an example number. So let's,
Go 1, 1, 0, 1, 1, 0, 1, 1.
I'll just pick this out of the blue.
Another one. There.
Looks like you're changing it now.
I'll tell you what, let's just go with that. That'll be different. Okay, so now we've got our binary number here, which I actually have no idea what it is in decimal at the moment, but I don't care because I'm going to go from binary to octal.
Alright.
Now all I do is if you have a look at octal, octal is base 8, binary is base 2. How many times does 2 fit into 8?
4 times.
4 times, or 2 cubed is equal to 8. So if I have groups of 3 binary bits, from the right, which is the least significant bit, each one of those is going to give me an octal character. So 1111 is the largest octal character, which is 7.
So what's the reason why you haven't chosen 4, like groups of 4 instead of groups of 3?
Okay, groups of 4
Yep.
means that there's going to be 16 potential states in that. 16 different.
So it sounds like it'll be too many for the octal
Too
system.
many. So remember, there's only 8 symbols. If we had 4 bits, there would be 16 to the power of 4 different ways I could arrange zeros and ones with 4 bits.
So the way I see it is octal is from 0 to 7,
0
which
to
means
7.
you can't
Yeah,
represent
there's
that.
8 different ways I can write zeros and ones in 3 of
So
them.
it fits.
Okay, so using that, I can go, right, I group my 3, 1, 1, 1, 1. Well, it's a 4 and a 2 and a 1, which is 7. 1, 0, that's a no 4s, a 2, and no 1s, so that's a 2. 1, 0 is a 4, a 2, and a no 1s, so that's a 6. Okay, so this number here is equal to 627 in base 8. Convert from binary to octal. And reverse from octal to binary is just as easy. I look at each digit at a time, 7, and I write it down in binary. So 7 in binary is 111. It's a 4 plus a 2 plus a 1. A 2 is 0 and a 2, 0, so it's going to be 0, 1, 0. And 6 is a 4 and a 2 and no 1s, so it's 1, 1, 0. You can see we've got the same number.
Alright, so just a question, you'll never have anything greater than 7 with a 624?
This number is not octal. That does not exist.
Yep.
It is not an octal number because...
So when you see that number, what do? Just...
Well, you realise that it's not an octal number.
Yep. So
it might be a decimal number, or it might be some other number. You can't be sure.
So it's a mistake, pretty much.
It's a mistake. So it falls outside of our character range, if you like.
Yep.
It's kind of like in decimal, all of a sudden saw a G, you wouldn't know what it meant. Okay? So what does G mean in terms of 110G? What's that mean? From binary to octal and back again, you group the 3 bits together. Binary to hexadecimal, well, you touched on it before when you mentioned why don't we group them in 4s, and that's because I'll use the same number. Binary to hexadecimal, we use the same idea, but instead of 8 symbols, we've got 16, which can be represented by 4 bits. Okay, so I group them in groups of 4. If I've got any left over, and this applies to octal as well, then I just precede them with zeros. In the same way that 5 is equal to 0.5. Group them in 4s and then write down what their hexadecimal equivalent would be. So 01111 is 7. 001. So I've got an 8, no 4s, no 2s, and a 1, so it's a 9. 0001, which is a 1. So this number here in hexadecimal is 197, and I can do the exact same thing in reverse. I'm going to choose a different number though now because I want to use one of these to show you how that applies. So if I have 27A as my hexadecimal number, all I do, in the same way that each digit in my hexadecimal number was represented by 4 bits, well, each digit here is represented by 4 bits as well. So I'm going to start from the right. A is 10 digitally, which I can make from an 8 and a 2.
10, 11, 12, 13, 14, 15.
And 10 is made from an 8 and a 2, so it's 1, an 8, a 2, and no 1s. That's my A. A 7, we saw 7 there, it's made from a 4, a 2, and a 1.
So 0, 1, 1, 1.
And the 2, again, is going to be
0, 0, 1, 0.
So that is 27A in base 16 is equal to this in base 2.
You make it look too easy.
It is pretty straightforward. And what it's doing is each time you press a different key, the computer sees a different binary number that maps towards this ASCII.
So why do we use 8 bits for the ASCII code?
Why do we use it? Because 8 bits has 2 to the power of 8 different characters, or different states that we could represent. So if we want, we could have 2 to the power of 8 different symbols.
Yep.
And 2 to the power of 8 is 256, which is a lot of characters, so we can put A to Z, capital and lowercase, 0 to 9, a whole heap of punctuation, some other stuff like non-displaying characters like line breaks and returning characters.
And space
like
and that.
Yeah, backspace, things like that. So we can, with 256 symbols that we at our disposal, we can use lots of different...
that seems like a lot on the keyboard, so
yeah.
we don't need more than that.
We don't see that on the keyboard necessarily, because some of them aren't necessarily there.
Yep.
Also, there are some things like allows, which is the dots above U's and things you see. Okay, accents.
So, grab A accent.
So we're going to look at doing a couple of conversions between, let's say decimal. Now I'm going to pick 100 and decimal number.
So I'm going to write that as 110 base 10. So that's decimal. Now we're going to
Convert it to binary and octal and hexadecimal. And remember, it's easy to convert to binary first, and then from binary into these ones.
Right.
So convert to binary, I'm going to use the remainder method.
110 divided by 2 is 55. Remainder 0. So the first on the right is 0. 55 divided by 2 is 27, remainder 1. So we got 1 there. And 27 divided by 2 is 13, remainder 1. We got another 1. 13 divided by 2 is 6, remainder 1. Another 1. 6 divided by 2 is 3, remainder 0. 3 divided by 2 is 1, remainder 1. And 1 divided by 1 is 0, remainder 1.
So 110 in decimal gives me this number binary. Okay, now we're going to convert to octal. So octal, we group them in groups of 3. So looking at the first 3, 110 is equal to, we got a 4, a 2, and no 1, so that's 6. The next group of 3 is 101. It's equal to 5, a 4 plus a 1. And we're left with, on the end here, a solitary 1, so 001, which is equal to 1. So it's 156 base 8. Again, pretty straightforward to go from this to octal, binary to octal. Hexadecimal, we do the same thing except we're now going to group in groups of 4. So the first one is 1110, so look at the right-hand most 4 there. And that is an 8 plus a 4, which is 12, plus a 2, which is 14. 14 base 10, which is equal to E base 16. So E is my least significant character. The next one is 110, 0110. So I've given it a preceding 0 again. And that is no 8s, a 4 and a 2, which is 6 base 10, which is also 6 base 16. So we're going to have 6E is our base 16 number. So we've gone 110 decimal is this number in binary, which is 156 in octal, and 6E in hexadecimal. Let's do one where we convert from hexadecimal to all the others. Okay, so let's look at C3 as being my hexadecimal number. Now, what I'm going to do, I'm going to convert to binary first, and then from binary to the other two. So C3 in binary, I look at each character one at a time and I just write down in 4 bits what the binary equivalent is. So 3 in 4 bits is 0, 0, 1, 1. C, which is 10, 11, 12, which is 1, 0, 0. And 8 plus a 4 is 12, and we know more. Okay? So this is the binary number. Just happened to make a palindrome, don't ask me how. That is the binary equivalent of C3. Now I'm going to convert it to octal. That's my easy one. Do the easy one first. So looking at the group of 3.
0, 1, 1 is equal to, so 2 plus a 1, which is 3. So the first one is 3.
We've got 0, 0, 0.
That's 0.
Left with 0, 1, 1.
Which is equal to 3 again. So.
Yet again, a palindrome. Okay.
How'd you pick that?
I don't know. To convert from this number, binary, to decimal, I'm going to look at, from the right-hand side, we're going to look at how many 1s, 2s, 4s, 8s and 16s I've got. So let's do it this way. So, and now I'm just going to write down how many lots of each one. So I've got one lot of it. So 128 plus 64 is 180, 192, plus 2, 194,
195.
plus 1, 195. Binary to decimal, I make a list of the powers of 2. So basically each one is just 2 times the next one across. And then I add how many lots of each one I have. So I've got one lot of 1, one lot of 2, no lots of 4, 8, 16, 32, one lot of 64 and one lot of 128. Add them together and I'll get my decimal number.
Bob's your uncle.
Bob's your uncle. And not a palindrome this time.
Yeah.
Convert from BCD back to decimal, pretty straightforward. I'm just going to pick some random number. Well, you want to pick a random number for me?
0, 1. Yep. 1, 0. Yep. 1, 1, 1, 0.
Okay, now notice how I separated them into groups of 4 bits. That's just for me. You may not see it like that. There might be just a string of bits altogether. All I need to do for this one is convert each group of 4 into its decimal equivalent. This one, I think we're going to find it's an invalid number. Let's see. we've got
Ooh.
an 8, a 2, so there's 10, 11. So this is 11, so it's actually going to be invalid.
So another
It's an
number.
invalid BCD code. Oh, I'm actually glad that you brought that up, because what would happen if that happened? This is what you would get. You would get, again, when we looked at what happens when we have too large a number on the 7-segment display driver,
Just goes
we're
blank.
going to see a blank bit there.
Yep.
So let's just modify this slightly and make that. Okay, so now we've got ourselves a BCD that is valid. So the first one here we've got an 8 and a 1, so that's 9. And this one here we've got a 4 and a 2, so that's 6. And so we have a 6, 9. To convert from BCD to decimal, you just look at the 4 bits and convert each of those 4 bits to a decimal number, and then that's each number or each numeral in the decimal number. Okay, so if BCD was 0, 0, 0, 0, the decimal equivalent of that is 0, and the 7-segment output would display the 5 segments that would give you 0. If we tick it over to 0, 0, 0, 1, decimal 1, you get the 1, 1. If we keep going, 0, 0, 1, 0, which is the next one, which is 2, we get the ones that represent a 2, so we get that one, that one, that one, that one, and that one. And you can probably see what's going to happen continuing on. So I'm going to skip a few. I'm going to get to 9, which is 1, 0, 0, 1, which is 9. So we get the 7 the segments that operate as that. Now some of them do this one, and some of them do this one. Now I think that just depends on which country you buy them from, manufacturer, that sort of thing. Now what's going to happen when we tick over?
Ooh.
I can't display that, so it's blank. There's nothing being shown. Okay, and that'll be the same for if I keep going. So when we get down to 15, but I've run out of states now, so it's gone through all my 16. I'm back to 0. Segments needed for that.
Cool.